Let's talk about the enantiomeric excess concept. When you do have chiral molecules, there is an interesting interaction between light and the chiral complex that you may be dealing with. In particular, there is this idea of the polarization of light. And to give you an idea, in this picture right here, you can see you have a regular lens that allows you to see the images in front of it, and you don't see much of a difference from the image without the lens and the one with the lens. But when you do have a lens that has a polarimeter disc on it, one that is going to filter out some of that light, you see a slightly different color or a slightly different overall look of what's in front of you with that particular filter. And in the context of doing this type of experiments, we have polarimeters, as the one shown here on the upper left corner, where you place a cell of your pure chiral compound, you pass light through it, and you make some determinations, as we'll talk about in a few minutes. This particular picture from the MIT physics department, I think is actually very visually indicative of what's happening. This tube contains pure sugar, which is chiral, and the light is being passed through it. So here's the source, right? So light is being passed through it, and as the light is making its way through the tube, the light interacting with that chiral substance is beginning to be rotated, and so you end up seeing different versions of that visible light being emitted, if you will, from the tube. So you kind of see the entire rainbow of color. Um, and as you'll find out, yeah, this idea of kind of rotating light, polarized light, is ultimately what we're going to be dealing with. And some molecules can actually have a lot of intricacies within it. It doesn't need to be like your simple carbon molecules that we're talking here. You could even have inorganic molecules, as depicted in this paper in communications, where you do have a chirality center on a metal, but that's more an inorganic topic. So we'll steer away from that. What you're doing in this type of experiments is technically using polarized light to be shined on a sample, and you see how the sample rotates the polarized light. So what you start initially is with a sodium lamp, which is excited, and the emission of light from the sodium lamp has different uh, wavelengths of light. Using a grating, you can select for the D line of the sodium emission to be passed through. And technically speaking, this light of the D line emission of sodium is unpolarized. So you have the rotation of the light every which way. But this D line emission is passed through a polarization filter, which allows you to have a unique polarized pattern of light. Now it's only in one direction, up and down, if you will, in this picture. And the polarized light is now what's passed through the chiral sample. The chiral sample rotates the polarized light um, by some degree. It depends really on what the sample is. But then what you end up doing, or what the instrument ends up doing, is it does have another filter at the end. And the filter will only allow the light to pass through if it matches up specifically with where this polarized light is being rotated. So the disk itself is allowed to rotate until it matches up with the polarization of the light, at which point the light reaches the detector, the 4-multiplier tube that converts the light source into an analog signal that is read by the computer. And if you have the R enantiomer, the light of this polarized D line is going to be rotated in one direction. If you have the opposite enantiomer, the rotation is going to be exactly in the opposite direction, but by equal magnitude. So this is something we want to keep in mind. And as far as rotation goes, we're going to use the symbol alpha. So the rotation for the R enantiomer is going to go in one direction. The rotation for the S enantiomer is going to go in the opposite direction by the same magnitude. And I'm referring to it by directions as opposed to saying clockwise and counterclockwise, because the unfortunate thing is that having an R enantiomer doesn't guarantee that the rotation of light is going to be clockwise. There's plenty of examples where the rotation can be counterclockwise, but the one thing that is constant throughout is that whatever rotation the R enantiomer has for the polarized light, the S enantiomer will be opposite in direction, right? So if R is clockwise, S is counterclockwise. If R is counterclockwise, S is clockwise. Okay, now thinking about what's happening to the light source. You have light that's coming in, interacts with your sample, and then it comes out of the sample. And what you're really seeing is how much the rotation of light is taking place as the incoming source is compared to the outgoing source. So in a way, you can think of this as a Beer-Lambert law, roughly speaking. I call it the Beer-Lambert law of polarimetry, where the observed rotation is in essence equated to the maximum rotation of the sample times its concentration times the path length through which the light goes through. The path length for polarimetry is actually in decimeters, whereas the concentration is in grams per ml. The observed rotation is, technically speaking, the multiplication of all these terms. The maximum rotation can happen at a reference value, which is taking place at 20 degrees Celsius, a concentration of sample of 1 gram per ml, and a path length of 1 decimeter. And so plugging in those values, 1 gram per ml for the concentration and 1 decimeter for the path length, gives us the maximum rotation. The observed rotation is equal to the maximum rotation under these conditions. But this is only if the sample is pure. Because if the sample is not pure, the observed rotation is going to be less than the maximum rotation. And you can kind of see that clearly by saying that, okay, if the sample is not pure, if you prepare a 1 gram per ml solution, then technically you only have maybe 0.8 or 0.9 grams of the substance in question present in the solution. So your concentration is actually less. Therefore, based on this equation, your observed rotation should be less than the maximum. Okay, now any polarimetry experiment is performed under this condition specifically. You use the de-emission line of sodium to make the measurement. You do make sure that your concentrations are 1 gram per ml, so you would actually have to prepare the solutions, by hand, so you have that concentration, and you use the 1 decimeter path length tubes so that your rotation is associated with the max rotation. And assuming your sample is pure, you can make a good judgment call as to what's happening with your sample. All right, but having purity of sample, as in you have the individual molecule isolated from anything else, doesn't mean that the samples are going to be enantiomerically pure. And what that means is that you could actually have a mixture that's pure for, in this case, 2-chlorobutane. But the 2-chlorobutane could in and of itself be a mixture of the S isomer and the R isomer. And if both of those enantiomers are present, then passing the polarized light through the sample, on the one hand, looking at the red enantiomer, you will rotate light in one direction according to the specifics of this enantiomer, but then the opposite enantiomer will do the opposite. It will rotate the light in the opposite direction. And depending on the concentration of these two substances, there's going to be a net effect as to how much the light gets rotated. In essence, the observed rotation from the pink enantiomer is going to be given by the maximum rotation of that enantiomer times its mole fraction. And the rotation for the red enantiomer is going to be given by the maximum rotation of the isomer times its mole fraction. And notice that I'm putting a negative in front of one of them because whatever rotation one of the enantiomer has, the rotation is going to be opposite, or the negative of the first. So in essence, one enantiomer is rotating the light in one direction, the other one is rotating in the other direction. To know how much the light's going to be rotated overall, you have to add these two equations together. So the rotation of the mixture is now going to be simply the maximum rotation times the difference of the mole fractions of the R or S isomer. Now, since technically speaking, the R isomer does not need to be the one that's present in greatest amount, this is more the absolute value of the difference between the two mole fractions for the enantiomers times the maximum rotation. This is what you're going to see for the mixture. And speaking of which, the difference in the mole fractions of the enantiomers times 100% is what we refer to as the percent enantiomeric excess. This will tell us how much of one isomer we have extra compared to the other one. And this is perhaps the simpler way to look at it. If you do look online or even in your textbooks, you'll see a different formula for this. But in my opinion, looking at the mole fractions and the difference in mole fractions is the easier way to define the percent EE, enantiomeric excess. So we'll use that for an analysis. Okay, so it's time to show you an example of how this ultimately plays out. Let's say that you do have a mixture, and in this case, this is a mixture of 1, 2, 3, 4. So this is butanol, 2-methyl butanol to be exact, and this mixture contains a 50-50% amount of the two enantiomers. Now notice that the maximum rotation, which the typical symbol for the maximum rotation is alpha in brackets, 26, and then D telling you that it's the D line, 26 telling you that's the temperature at which the experiment was carried out. You have a rotation of plus 5.75 degrees and then a rotation of negative 5.75 degrees, implying clockwise rotation, counterclockwise rotation. All right, so what we want to find out here is what's the final observed rotation of this mixture, the 50-50 mixture, and what's the percent enantiomeric excess. In order to answer these questions, first things first, we need to determine the mole fractions. 50% of each enantiomer means that out of 100, which is the sum of the two, 50 is what you have for each enantiomer. So 50 divided by 100 is the mole fraction, which is 0.5. And the S enantiomer, same idea. You could divide 50 by 100 or make use of the fact that the sum of the mole fractions has to equal 1. So subtract the mole fraction of the S, or in this case the R enantiomer, from 1. That gives you the S enantiomer. So unsurprisingly, they both are 0.5. Okay, now looking at the formulas, the observed rotation for the mixture is going to be the maximum rotation times the difference in the mole fractions. And the percent EE is going to be the difference in the mole fractions times 100%. In the case where you have 50% of each enantiomer present in your mixture, well, what you can see right here based on the mole fraction differences is that, well, you're going to get 0, right? Because 0.5 minus 0.5 is 0. Doesn't matter what you multiply by it. 0 is always going to be 0, right? So what this tells you is that in a mixture where you have 50% of one enantiomer and 50% of the other one, the light will not rotate whatsoever, because whatever rotation happens for the R isomer is going to be undone by the rotation of the S isomer entirely. And the percent E is automatically 0. You don't have an excess of either enantiomer. They're both present in the same amount. So this is perfectly stated by this equation. And this type of mixture, it has a specific name. We call this a racemic mixture. Technically, it contains chiral molecules, but it contains equal amount of both enantiomers. Okay, so let's see what happens though in a case where we actually do have an enantiomeric excess. So let's say that there is 50% enantiomeric excess. And I want you to be careful with not confusing this with what we just said in the previous example. 50% enantiomeric excess is not the same thing as saying that you have 50% of each enantiomer. And I'm going to show you with equations exactly what that means. 50% enantiomeric excess, based on the equation, we know that the percent EE is equal to the difference in mole fractions times 100. So knowing that the percent enantiomeric excess is 50%, well, we input that in here. 50% must equal the difference in the mole fractions times 100%. Dividing both sides by 100 tells us that 0.5 must equal the difference in the mole fractions. And here's where we make use of the fact that adding the mole fractions together, we must have 1 as the resulting value. Therefore, the mole fraction of S can be rewritten in terms of the mole fraction of R. Specifically, the mole fraction of S simply has to be 1 minus the mole fraction of R. And what this basically does for us is it turns an equation that had 2 unknowns into one that only has 1 unknown. Distributing the negative tells us that we have x minus 1 plus x. So x plus x will give us 2x minus 1. And if we add 1 to both sides, we're going to end up with 1.5 equaling 2 times the mole fraction of R. Divide both sides by 2 and you're going to find out that the mole fraction of the R isomer is 0.75. Subtracting 0.75 from 1 tells us that the other isomer is going to be 0.25. Now, technically speaking, I am assuming that the rotation was positive for the maximum of observed rotation of the sample. Because if the rotation would have been negative, then technically speaking, the S isomer is going to be the one that's greatest in amount. And so the S isomer will be 75. So this kind of depends on what the observed rotation for the mixture is. If it happens to be positive, as you'll see in this case, then the mixture is definitely what we have right here, right? So R is going to be the one in greater amount, S is going to be the one in lesser amount. We have 0.5 for the subtraction, multiply by the rotation of the R isomer, and you get yourself the rotation of the mixture. So in the mixture that has 50% EE, we're going to expect to see a rotation of 2.87. And these are the actual amounts. So as you can see, the equations are rather robust in telling us how much of the R isomer we're going to have, how much of the S isomer we're going to have. And I would like you to use these equations for future calculations. And for those of you who may be basing your calculations based on your book, which has different equations than the one I'm presenting here, I want to assure you that what you are seeing right here works every time. So you're more than welcome to adopt these equations in your calculations. Okay, so this concludes this video. In the next one, we're going to talk about the situation where there are multiple chiral centers present in a molecule.